Hello everyone, I'm Shr-Ruei from National Yangming Jiaotong University. I'm here today to present our work, LightsOut Diffusion-based Outpainting for Enhanced Lens Flare Removal. This work is a collaboration with my lab co-workers, Wei-Cheng Chang, Jie-Ying, Chih-Hai, and my advisor, Professor Yu-Lun. Lens flare is a common yet difficult problem in computational photography. These artifacts severely degrade image quality and negatively impact downstream computer vision tasks. In recent years, the field of single image flare removal has developed deep learning-based methods to address these artifacts. We have seen influential strong contributions over the last few years, like the methods from Wu et al., Zhou et al., MFDNet, Difflare, and the Flare 7K series. However, while existing single-image flare removal models offer impressive capabilities, we identify a critical and fundamental limitation. To illustrate this issue, we take Flare 7K++ as an example. We observe that the model often produces unnatural artifacts when the light source is partially cropped or completely outside the frame. Consequently, the model struggles to remove the flare effectively, since it lacks sufficient information to infer the true light source location. As discussed earlier, the existing approaches heavily rely on complete light source context. Wait, go back! Alright, let's revisit this, but this time using our approach. Our goal is to solve this incomplete light source problem. To this end, the limitation motivates us to come up with an outpainting method. The core idea is simple. Before performing flare removal, we first apply an outpainting strategy to reconstruct the missing light source and background context. After that, the outpainting images are fed into existing models to handle the flare removal. We obtain flare-free results from the outpainted images. To restore the framing, we crop out the extrapolated regions, returning the image to its original size. When we zoom into the edge regions in the original input, we can observe that when the input includes the complete light source, the result demonstrates better restoration quality. Here, we compare Flare 7K++ with our method. As you can see, we significantly reduce residual flares and maintain more natural illumination. Next, to validate our observation, we evaluate different methods on other real-world images. Interestingly, with complete light sources, all three methods effectively remove lens flare. In scenarios lacking complete view of light sources, however, all three methods degrade. This further highlights the motivation behind our work. This is a brief overview of our method, LightsOut. Given an input image with incomplete or missing light sources, our model first predicts the most probable position of the light source as the condition signal. Next, we open the off-frame light sources to reconstruct the complete image. Subsequently, single-image flare removal models are applied. As demonstrated, integrating our outpainting strategy as a pre-processing step enhances both flare removal quality and the overall visual realism. To summarize, our main contributions are as follows. First, we identify and address a key limitation of flare removal methods through a specialized decomposition strategy. Second, we propose a LoRa fine-tuned diffusion-based model that accurately reconstructs physically consistent off-frame light sources and flare artifacts. Finally, we introduce a plug-and-play preprocessing framework that universally boosts existing models without additional retraining. Let me introduce our method details. In stage 1, given an input image, we first define its outpainted region. The mask image goes through our light regression module, which predicts the light source parameters, including positions, radius, and confidence scores. These predicted parameters are used to guide a rendering function that generates the corresponding light source mask. Move on to stage 2. We leverage a LoRa fine-tuned diffusion model to do outpainting, but this model requires proper conditioning. Using a pre-trained vision language model Blip2, we generate customized text prompts that describe the image context. In addition, we train a control net from scratch to serve as the light source conditioning module. Finally, we apply noise reinjection to ensure accurate and coherent outpainting results. Moving to next stage, the generated outpainting image is passed into single image flare removal model. Then we use the mask from the beginning to crop out the extended areas and return the image to its original size. We test our approach on the Flare 7K testset in 2 scenarios. First, when there is no light source in the frame, and second, when the light source is incomplete or cut off at the image boundary. These 2 cases help us evaluate how effectively our method recovers missing light information. We compare several state-of-the-art single-image flare removal methods, both on their own and combined with our approach, under 2 challenging scenarios. We also present additional outpainting results on self-collected in the wild scenes. And that's it. Thanks for watching. Please check out our project page and paper for more details and results.